You're the boss.
Welcome to everybody to this morning session. So the first speaker for today will be Mark Pollicott from University of Warwick, UK. He will talk about the hyperbolic dynamics perspective of flat surfaces. Please, Mark.
Thank you very much. Let me begin by thanking the organizers for their kind invitation and the opportunity to speak. And let me say it's very nice to be here at this nice institute and with its excellent gardens and good weather except when it rains. So I should perhaps explain the title before I move on. So by flat surfaces, I mean surfaces which have zero curvature, or translation surfaces, as they're sometimes called, a subject about which I know epsilon. And so therefore, I'm going to take a perspective where I try to force into this model my own particular interests, which are more on hyperbolic dynamics. Whether it succeeds or not will be a matter for you to judge. So let me start off. That worked. Okay, so classically, in ergodic theory, a very successful model has been the geodesic flow. Usually on negatively curved spaces, due to the fact they tend to be ergodic, and in ergodic theory, things that are ergodic tend to be easier to study. And in this context, particularly important quantity is the topological entropy, which is a numerical value that tells you something about how chaotic or complicated your system is. And it's useful for various things. One is that it tells you how various quantities grow. It's a growth exponent for aspects of the dynamical system. That's one particular application. And another one that I want to push is the fact that it can be used for rigidity results. That is, amongst some class of dynamical systems, there might be ones which are of particular interest, and they are identified by the fact that their entropy takes a certain value. Maybe it's the minimum over the class, something like that. So the entropy is a is a useful sort of invariant, and it's particularly useful in the context of negatively curved surfaces, which are classical examples of chaotic dynamical systems, for these two reasons. It quantifies how things grow, and sometimes it tells you how to identify particularly interesting examples. Like all overviews, I'm being extremely vague. Some of this will become a bit clearer, hopefully, when I move on. And the question I want to ask is, can you do anything analogous to this in the context of flat surfaces, that is, surfaces which have zero curvature? So first of all, it doesn't seem very promising because it's not clear how you could define a notion of entropy which wasn't always equal to zero. That would seem to be rather fatal. So one has to come up with some appropriate definition. And secondly, one has to show that it's useful for something. So that's my goal in this outing. So as I just said, I mean, the easiest example you can think of a surface which has got zero curvature is just a flat torus. So if you just take a square, or possibly an oblong, and then you identify all the opposite sides, which is kind of hard to do with a piece of paper. If you roll it up and you get a torus, then it's got zero curvature. And so this is not a very promising example. But if you have slightly more complicated surfaces, then what happens is you get singularities, which I'll explain a bit later. And these save the day. This allows you to come up with a notion of entropy, a numerical invariant, which tells you something about the surface. And here's the warning saying that I'm not an expert on translation surfaces. I don't actually think of myself as an expert on anything in particular. I'm just a jobbing mathematician, and at the moment I'm just trying to explore this concept as best I can. So let's go back to negative curvature for the motivation. And so this is meant to be a picture of a surface of negative curvature. It's got genus 2, so it's got two holes. And we can assume it's got negative curvature, so the Gaussian curvature is going to be negative at every point. I like the way the cursor moves very slowly. It's very leisurely. And so what do we do then? Well, we look at the geodesic flow. So the geodesic flow is not on the surface, but it's on the unit tangent bundle. These little vector guys here. Here's a point and here's a vector. and it's going to go to this vector. And it flows in the usual sort of way, which is that you take your point and the unit tangent vector here, and you just push it along this geodesic in the direction it's pointing. And that's the geodesic flow. Easy. And you can do this. Hello, how are you? Good morning. It's nice outside, isn't it? And so you can associate to this a numerical value, which is the topological entropy. It's some quantity which in this case will be strictly positive. And it's got some definition which usually exasperates my students, because the usual definition is to use epsilon separated sets or epsilon spanning sets, and they don't like those very much. It's too complicated a definition. The picture on the left is a cover from the proceedings of a conference in 1989 held in Trieste, right country. And the picture on the front is actually drawn by me, because I wrote an article in this proceedings and they seemed to think it was so good they put it on the cover. So that tells us that 33 years later I haven't got on very far from these things, which could be a bit depressing. Okay, so let's assume that you're at a cocktail party with a geometer. They go to cocktail parties. And you want to tell him what topological entropy is, and he doesn't want to know about n epsilon separated sets or spanning sets. It's far too complicated. So how are you going to explain it to him? So here's the surface again. I'm still in the negative curvature setting, and I choose a point which I've called x0, but not indicated on here. It's that point in the middle. Just any old point on the surface, I don't care where. And I'm going to draw a circle around it of radius r. At the moment, r is kind of small, as you can see in this picture. It's kind of a small circle. And the radius r means that the central point x0 is connected to all the points on this, this red circle, the circle of radius r, by geodesics of length r. So far, so good. And if r gets a bit bigger, then what happens is that the circle gets bigger, as you'd expect. And as it gets bigger and bigger and bigger. And if r actually tends to infinity, then what will happen, it will spread out like a ripple on this surface, and it will start intersecting with itself, because the surfaces I've drawn are all compact. This radius is getting infinitely large, and so it will get kind of complicated. It will start self-intersecting. Something I didn't have the courage to draw on the slide, because it would take forever to draw these curves. Anyway, but that doesn't matter. You can do that. And how does that help us? Well, then the topological entropy for the dynamical system, the geodesic flow, is actually the rate of growth of the length of this circle. Circle gets bigger, it's going to infinity. How fast does it go? It goes exponentially fast. And the rate at which it grows is just the topological entropy. So you take the logarithm of the length of the perimeter, you divide out by r, let r tend to infinity. As we say in English, Bob's your uncle, which I think means that you get the answer, which is that it's the topological entropy. And this is just a variant on a definition by my now retired colleague, Anthony Manning. So that's a definition we can take for the topological entropy for the geodesic flow on the surface. It's a number associated to the surface through the dynamics. Okay, so far, so not so difficult. So now we want to consider flat surfaces. So the first issue is I'm not actually going to be very specific about the definition of these flat surfaces beyond the fact that they're flat, but I will illustrate it with two examples, because examples are always more illuminating than abstract definitions, perhaps. But the basic principle is I'm going to take something which is going to have zero curvature. It won't be just the standard torus. It will be slightly more complicated, and then the complications will give us singularities which will save the day. And then we're going to define a notion of entropy. How are we going to define the notion of entropy? We'll do exactly the same thing. We'll take a point and we'll look at bigger and bigger circles on the surface. That is, a circle which is connected to some fixed reference point by a geodesic on this surface, and I'll see how fast it grows. And that will give me my definition of topological entropy. Okay, and does this have anything to do with hyperbolic dynamics? Well, the answer is yes, because in the proofs, everything is proved using symbolic dynamics. I'm kind of hoping I'll run out of time before I get to the proofs, because I always get lost in proofs in talks. But if I'm not that fortunate, then I'll say a little about how this proof goes. But the essence of it is that it's all symbolic dynamics and stuff like that, and it drives it in the same way that the results come in the context of strictly negative curvature. Okay, so this is kind of waffle, me talking about stuff. Let me try to be more specific. So here's an example of a flat surface or a translation surface. It looks like a letter L, and I attempted to put lots of colours in, which of course in Beamer slides the colours are not always that easy to see. But the principle is that we take this shape, which is an L shape in the plane, and different portions of it are coloured in different ways. And the idea is, just like the standard torus, where we identified opposite sides of a piece of paper, we're going to identify opposite sides of this region. So for example, this side will get identified with that side, and this red bit, which you can see more clearly, will get identified with the other red bit, which is over here. And this blue bit will get identified with the blue bit at the top, and the green bit will be identified with the green bit at the bottom. You just stick all these bits together using Scotch tape or something, and what happens is you get a surface which is now going to be a compact surface without boundary. But what happens is, because it's more complicated than just a flat, just a square, it's more complicated shape, what happens is that it gets crumpled up at one point. And what happens is that all of the corners that you see, of which there are several, all the corners you see here and these points, they all get identified to the same point. And at this point, it can't be smooth, because there's things like the Gauss-Bonnet theorem that tell you that if the genus is high, then the curvature can't always be 0. And so what happens is that it gets crumpled up at this point, and this is a so-called singularity. It's a cone-type singularity with angle 6 pi, whatever that means. I'll explain that in the next slide. So that's the sort of surface that we might be interested in. Okay, so far so good. And so, as I've said here, that we're identifying the different sides, and the corners get identified to a single point whose total angle is equal to 6 pi. What does that mean? Well, it means that if you had an ant, this ant is a bit large, but if it was a smaller ant and it wanted to walk around this singularity, it might start down here on the blue bit and start walking around to this red bit, and then it would reappear on the other side, and it would continue walking around to this green bit, and then it would reappear at the top, and then it would walk around to this red bit, and then it would reappear on this side. It would continue its journey onto this black bit, then it would get identified over here. It would continue its journey around to this green bit. And as you can see, if you keep doing this, eventually you come back to the same place, but you've gone around 6 pi radians rather than the 2 pi, which a more pedestrian ant would prefer. So this is what's happening at that particular corner. Everywhere else is just like you'd like it to be. It's just like a flat Euclidean space. It's just at this one point that life gets a bit more complicated. Okay, and so what happens is that the surface has got genus 2, just like the picture I had on the cover of the book, except it's got 0 curvature everywhere, except at this one singularity where you've got all these angles stuck together. Okay, so that's an example. Here is another example where I've now got two parts. So now it's like having 2 pieces of paper instead of 1. See, I've got props for the occasion. And you do the same game. You identify the different sides. So you can see that in these 2 pictures I've got here the 2 squares. If I use the standard identification, then what will happen is for each of these 2 squares, I'll get a torus, but I'll also have this slit in the middle, for which I've forgotten to draw the colours on it properly. And then what will happen is that the slit will be identified with itself, particularly if I've done the colouring properly. Anyway, so in this way you get a surface which has got genus 2. You get a hole from each of the 2 tori, and it's just stuck together. And it means exactly the same thing if you had an ant walking around one of these singularities. There are 2 singularities at either end of this slit. If you had an ant walking around here, then it would fall off into the other picture down here, and it would gain an extra 2 pi. So it would take 4 pi to go around this particular singularity. So life is strange at the singularities, but everywhere else it's very, very Euclidean. And this is an example which you can actually make, sort of, if you're so minded. So if you take your 2 pieces of paper, like that, then you can make a slit in them simply by tearing it. There could be audience participation if you have any paper, but if you don't, you can watch me tear up pieces of paper. Very entertaining activity, especially if I had the physical strength to do it nowadays. And then now you have 2 pieces of paper, each of which has got a slit, and then you'd like to glue them together along the slit, like that. Or if you've done it yesterday, then you'd have the 2 surfaces like this. This will be 2 separate tori. I can't actually identify all the sides, but you'd identify these ends to get the 2 tori, and they're glued together along this strip like that. And then the singularity that you see at the corners just corresponds to your poor ant walking around this singularity, disappearing out the back, coming around here, and then going through again. And that's just another example of a simple translation surface. So those of you that want it in color, hi.
Sorry. There's 2 singular points with this slit gluing, or it's all 1 singular?
It's 2 singular points. So this thing that looks like the kind of thing you get Kleenexes out of, at the top, this is 1 singularity, and this is another singularity. So you go around here, and then you reappear on the other side. You don't interfere with the other hole.
2 or 3 pi?
Well, you get 2 times 2 pi. I mean, it's 2 pi for Euclidean space, and you're going around both surfaces, so it doubles. 4 pi, and the same thing at that side. It's exactly symmetric. I don't claim the arithmetic's perfect, but it's my best bet. Okay, and if you prefer it in color, here are some color pictures of the same thing, and hopefully, and this is just the 2 things identified, and then somewhere I have a picture of 2 donuts stuck together, which is basically what you're doing. So these are just 2 examples of translation surfaces. We don't need to worry about the fancy definitions. I don't worry, you can worry, but we don't really need to worry. We're just trying to get used to this concept. Okay, so what we'd like to do is we'd like to look at the growth of circles. So what is a circle going to be? It's going to be like it was on the negatively curved space. I'm going to specify a point, and then I'm going to look at all the points which are at a distance r from that particular point. And what does it mean to be at a distance r? It means that the central point, the center, is connected to every point on this circle by a geodesic of length exactly r. Doesn't have to be distance minimizing. Locally distance minimizing, yeah, but it's not going to be the shortest distance. It's just going to be a distance which, by a geodesic joining the center to the edge. It's exactly like the pictures I drew before, and that's what I want to do in this particular case. Now, what do geodesics look like on our flat surface? Well, first of all, there's a complication because of these singularities. And so the easiest case is if you start at some point x0, then if you don't go to a singularity, you don't hit a singularity, you just go on a straight line, then of course it doesn't make any difference. You just go in a straight line in the usual Euclidean sense, like that. But there are complications, because if you go from the singularity, sorry about that, to another singularity, that's another possibility. That would also be a geodesic. I could start at a singularity and go to another singularity. I could wind around the flat surface lots of times on my way there. It's possible, but that's a second possibility. And the third possibility, I guess, is that I might start, and I might go through a sequence of these lines between singularities, which are called saddle connections, and then eventually I just wander off for some period of time at the end. So a typical kind of geodesic on my surface is going to be a sequence of these saddle connections, that is, straight lines on the flat surface beginning and ending at a singularity, followed by just a piece of a straight line on the surface. So this is kind of a bit of geometry, but not perhaps too complicated. So that's the possibilities you can get. And these are the things I'm going to use as radii for my big circles on the surface, I claim. I'm also claiming if I push this button enough, it will change the slides. Okay, so the definition is going to be, I'm going to define a big circle on my surface. It's going to wrap around a lot, and it's going to consist of fixing a point x0 and looking at all the points on this circle which are joined to this point x0 by a geodesic. And the geodesic might be just a straight line on the flat surface, or it might be a combination of these paths which zigzag between the singularities. These are all possibilities. And the definition of the entropy will be exactly the same as it was in negative curvature. I'm going to look at the length of this, is it the circumference? I suppose it might be. The length of the curve, the circle, maybe it's the circumference, and I'm going to look at the growth rate of that. Except possibly where it says t on the bottom, it might actually be an r. I'm betraying my enthusiasm for hyperbolic flows and t is time, whereas if it was an r on the bottom, it would actually be consistent with the definition. So it's the growth rate of the perimeter of this circle. And that's the definition. So the first question is, why isn't it equal to 0? I mean, you know. Oh, and here's a picture, proving that I don't read my slides very carefully. I can't remember what's on each consecutive slide. So these are these large circles crisscrossing the surface. So as they got bigger and bigger and bigger, you end up with these pictures. So the one on the left, of course, is the L-shaped region. The one on the right is just made up of these two pieces with slits stuck together. You can't see the yellow particularly well, but on the red ones on the L surface, each of these curves is related to a part of this very large circle. It started off as a normal sort of circle. It got bigger and it got more complicated as it wrapped around. And its total length is growing in a way which defines the entropy. So this definition of entropy is kind of related to a definition by a guy called Dankworth from, I guess, 2012, so it must be true. He didn't define it the same way. He defined it in terms of growths of these paths between singularities, but it's the same thing basically. And as it says here, the fact that this picture is looking kind of complicated, it's really just one long circle which is self-intersecting, and it doesn't affect the definition of length. So let's go back to the question. So why is the entropy going to be positive? Why do we get exponential growth of this perimeter of this circle? And of course, it's because of the nature of the singularities. So let's imagine that I started my circle quite small, and I started it at one of the corners of this shape. And as I said before, this shape has got all the corners are identified, so my circle is actually going to have 6 pi angles because I'm starting at a corner, but the corners are all the same, they're all identified, and so I can go in any of the directions indicated by these little dotted lines. So my circle starts out having radius, I guess 6 pi times whatever the length of that arrow is, and as the arrow grows, it will start off growing linearly. So we try that for a bit, and it gets bigger. I've only drawn in the image from one corner. And when it hits the next singularity, then it starts splitting up. You get bubbles occurring, because when you hit the next singularity, then the curve I've just drawn takes me from one singularity to what is in fact the same singularity, but a different part of a point representing it. And then each of these dotted lines here still represents a continuation of a geodesic. So there are 6 pi different ways you can go when you get to the singularity. You lose 2 pi of them because it's not a geodesic in those directions, but you've still got 4 pi different ways to go. So the
curvature should remain the same, no? Of all those bits.
Well, yeah, indeed. My picture is, okay. Well, no, they're still circles based at the vertices, yes, singularities. But yes, I mean, what happens is that you get this bubbling effect which occurs every time you see a singularity. So we started off with a small circle, it got big enough to reach the next singularity, And then what happened is that the continuation from that, well, it includes these extra paths you get afterwards. And so what happens is that you get these smaller circles bubbling up, but they're really part of the larger circle. And so therefore you can define the entropy in that way. And I thought I was going to do another visual effect. So here's my piece of paper again. And if you imagine this lanyard as being a geodesic, then the point is that if you go into one of these singularities at some particular angle, there's still 2 pi different ways you can come out the other side. So that's why having a single path going into a singularity gives you this bubbling effect. You can still go out in lots of different ways out here, which is why you see these circular arcs appearing at the singularities. So the definition we gave before, the growth rate of the circle, the perimeter of the circle, gives us a quantity which is positive. It's the topological entropy high.
Question. Is it obvious that this definition is independent of the point, the center?
It's not too difficult to show it's independent because you can just choose 2 different points. All my surfaces are compact, so there's only a finite distance between them. And since we're measuring the growth of things, a bit of triangle inequality, I think does the job. So it's not too difficult to show, assuming it's true. Right. Okay. So this is the definition of topological entropy, and it mimics what we did for negative curvature, or what other people did for negative curvature. So the question is, what else can we do that people used to do for negative curvature in the context of flat surfaces? And so the first result is, well, we can improve on the speed at which this circle grows. We know it grows at an exponential rate, which means we take the log and we divide by the radius, and then the limit converges to h. But in fact, you can prove an asymptotic formula, which means that, in fact, the perimeter itself grows at a rate which is given by a constant times e to the h times r. So if I took logarithms in this, I would recover the entropy formula, which is the rate of growth. But this is just a genuine asymptotic, which tells you that the circle actually grows essentially like a constant times e to the h times r being the radius. So that's one thing one can prove. This is kind of analogous, so it improves on, as I was saying, it improves on just taking logarithms, checking the time. It's analogous to what happens in negative curvature. So in negative curvature, we defined the entropy in a certain way, but in fact, there are results that prove that it's asymptotic, as was proved by Selberg in the case of constant curvature, and written up by Huber in 1959, and Margulis in his thesis in 1969. So that's all in negative curvature, but the same results here are possible if we interpret entropy in this particular way. So that's one result. It's an extension of these kinds of asymptotic things. Oh, you might ask, if you think about the pictures I had on the slides before, I won't risk going back, you have to remember them. They had this complicated crisscrossing of the circle as it cut across the surfaces. Well, you might ask, are these circles equidistributed in some way? I mean, they look to be dense, getting denser. So are they becoming equidistributed in terms of the Haar measure or something, or Euclidean measure or something? And so you can paint around the perimeter of this circle just a one-dimensional Lebesgue measure, which is meant to be represented by this formula here. It's just saying you integrate around the circle with respect to the arc length parameterization. That just means the natural length. And so it means that on these pictures, the contribution from each of these red lines is going to be more or less the same for each unit length. And you can ask, well, is it evenly distributed on the surfaces? And the answer is not quite. The measure does converge. So you fix a point, look at a big circle, it gets complicated on the surface, but we're looking at how it's distributed on the surface, and it does converge to some measure which I've called mu, and this measure is absolutely continuous, but it's not the same as the area of the surface. And the reason for that, of course, is because the exponential growth is coming from these singularities. So as you look at a long part of the circle, there's a disproportionate amount of it which is coming from the last time it saw a singularity. And so what happens is that the density kind of builds up more around the singular points than it does on the rest of the surface. That's kind of intuitive. So there's an equidistribution result in this particular way. And if you ask for the analogous results for, say, negative curvature, then there's a result by Randall which does this. He proves that for a Riemann surface, constant curvature -1, take a point, look at a big circle, then it's distributed on the surface according to the Haar measure. Because there's no singularities to make your life more complicated. Okay, so these are just variants on the asymptotic results we saw for, or remembered for, negative curvature, which we're just extending using our funny definition of entropy to the context of flat surfaces or translation surfaces. Okay, those of you who can read the numbers at the bottom, I'm not going up to slide 29. I should explain that there's lots of stuff at the end that's there in case I went too fast, which I don't plan to do. And what I want to do now is talk about the second application of entropy I mentioned before, which is this rigidity result, which will be the next slide. So,
can I just ask?
You can.
Does your equidistribution result also hold at the unit tangent bundle?
Yes, it will converge, and it should also converge to something, but I'm not entirely sure I can specify what it is. Yeah, yes.
That's good. Did you compute C?
Compute what?
The constant.
The constant C, you can...
It depends on the surface, right?
It does depend on the surface, and it also depends... Well, it also depends on where you are on the surface, I think, as well.
You start from...
If you start from the singularity, then of course there's only one choice in the first example. But no, I didn't compute it. I'm too lazy to do calculations. But I mean, yes, it should have a specific constant. I mean, in the case of negative curvature, it's got an interpretation in terms of the Margulis measure, blah 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 blah. And in this case, it won't, but it will have something that comes out of the proof. So it can be computed. No idea what it is. I think that's the short answer.
Excuse me.
Yes.
So you mentioned that this Wick-Star limit is not the Haar measure on the surface.
Yeah.
It's heavier near the singularities.
That's correct.
So the cone points that have different cone angles, do you see the difference of the weight?
You should do. So what will happen is the density will be a superposition of what happens at different singularities. So if you have one singularity, it's fine, but it's going to have rippling effects as you look further and further away. So if you have finitely many singularities, then indeed you'll have different concentrations of these more dense rippling effects, presumably at different singularities. That was a very incoherent answer, but I think the answer is yes. You should be able to identify it in some way. But no, I haven't done it. Okay. So let me just move on to the second application. So entropy is a growth rate. It tells you stuff. That's fine. What about rigidity theorems? And so a kind of famous sort of rigidity result, which is due to the late great Anatoly Katok, was using entropy to say something about surfaces of negative curvature. And so the game there was that you take a compact surface of genus 2 or something, and then you look at all metrics on it which have the same volume, say volume 1. Let's normalize it to that. And then for each of these metrics we can look at the entropy for the geodesic flow, and we can plot the entropy over the space of different metrics. Now the space of different metrics tends to be kind of infinite dimensional, but I've drawn it as a two-dimensional picture, because I can't draw infinite dimensions, and 2 dimensions is the limit of my drawing ability. So this represents at the bottom, let me point to the screen when I could use a pointer. Oh, it moves very slowly. So this black square at the bottom is meant to represent all possible surfaces of variable negative curvature. For each of them I can associate a geodesic flow, for which I can associate the entropy, and then I plot the entropy in the vertical direction. And the result of Katok in this case is that once we've normalized by the area, the topological entropy will always go up if you start from constant negative curvature. So you can identify the metrics of constant negative curvature, the Riemann metrics, precisely by the ones that minimize the topological entropy. So this is a classical result of Katok from the early 1980s. It's actually relatively easy to prove, but I mean, if you didn't know how to prove it, it would be harder, so it's a nice result. But once you've seen the proof, it's not so difficult to do. So what I would like to do is to try to formulate some analog of this for flat surfaces. I'd like to say, here's a flat surface. I have this numerical value related to the surface itself. If I kind of do something to the surface, maybe the entropy will change a bit, and maybe I can use that to characterize particular kinds of surfaces. That's what I'd like to do. Can I do that? No. But I can attempt to do something. And what I'll attempt to do is to look at some specific example. And I'll go back to the L-shaped. I keep wanting to say L-shaped room, which is a book, but I don't think that's very appropriate. So here is my L-shaped surface. The red dots are the singularities. And I'm assuming that I start off with the surface consisting of just unit squares glued together like boxes in this particular way. And again, it gives me a translation surface, a flat surface, just by identifying opposite sides. That side, this side with that side, top side with bottom side, blah, 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 stuff like that. And that would give me a specific surface. And then I want to ask myself, well, how can I change the surface in a way that will change the entropy? And the easiest, well, one way to do that is to squash it or shear it or do something to it by changing the plane. It sits inside R2. So if I take a matrix in SL2R, 2 by 2 matrix, determinant 1, real entries, then I can change the entire plane just by multiplying vectors by this matrix. And this effect on the plane will also have the same effect on the surface. That's the game. And so the example, the first example is I took the matrix, which is diagonal, and I apply that to the plane, and of course it squashes it in one direction and stretches it in the other. And so the effect on the surface is that my flat surface topologically looks the same. It's got the same identifications, but now it looks kind of fatter in this direction and shorter in the vertical direction. So it's changed. And in the second example, let's move to the second one. I multiply the plane by this matrix, which is 1, alpha, 0, 1. And this has the effect of shearing the plane. Everything leans over. For some reason I'm thinking of Pisa, but I don't know why. And so I get this surface here, maybe. Same identifications, but its geometry has changed a bit because I've sheared the entire plane. So they're topologically all the same surface, but the distances have changed. And so more generally what I'd like to say is, can I study the entropy for every surface that I can get by multiplying my original surface, this guy, by matrices, so it's like a subspace of all possible ways of messing around with these things, and looking at these entropies, can I say anything about where it's minimized? Just like our good friend Anatolia did. And, well, you can say something. So the first observation is that by multiplying by SL2R, it doesn't change the area at all. So it's just like in the constant curvature case, we're looking at surfaces of the same area. And that's good, because it's analogous in that sense. And a second thing that's useful is that this entropy, whatever it is, it changes smoothly as we change the surface, as we apply these matrices. So it makes sense to draw these pictures as they looked kind of continuous. So it's completely analogous in that sense. And the result is that, well, yeah, you can start off with your original example, the L-shaped region. You can deform it by applying these transformations from SL to R. And what happens is that there are particular surfaces in this orbit which minimize the topological entropy. And they turn out to be the surfaces which are triangulated by equilateral triangles. So in the shearing picture, if we sheared by some angle and flattened it down a bit, then we get an example where we get this tiling by equilateral triangles. You can see I've got these dotted lines here. You can't see the dotted lines very well, but that's what divides these quadrangles into triangles. So in each of these pictures, these are the examples when we look at the definition of the entropy in terms of the growth rate of these big circles, then it's minimized for these particular examples. Okay, and the intuition here is that, oh, hi.
Those two surfaces are equal because if you do cut and paste, you can transform the one into the other. So is that correct?
It's correct that some of them can be identified and some can't, and I never know which ones are which. So let me say there are two surfaces in this orbit which are distinct, but I'm not guaranteeing that it's these two. Yeah, so I take you back to my warning on the first page. I'm not an expert on translation surfaces. So whatever the surfaces are that minimize this globally, the topological entropy, they are triangulated by these equilateral triangles. And the intuition is that the entropy grows very quickly if you have singularities that are very close, if you have a short saddle connection, a path between singularities. And so somehow this is the one where the singularities are most spread out on the surface. I'm not sure it's a very useful intuition, but it's what it is. And so here's a plot of what the entropy looks like on the orbit under shearing or under flattening. So I mean, I'm back in 2 dimensions, and you can sort of imagine that there are 2 minimum in here somewhere around about here and somewhere around about here, which minimize the topological entropy. Anyway, so that's the sort of analog of the result in the context of flat surfaces. It's not so great in the sense that it only deals with one particular family. That is where you take the original, well, it's not great in the sense that it starts off with a single surface, which is the L-shaped surface, and secondly, it's not great in the sense that it's only on the orbit of that under SL2R. It's not a more general result than that. Let me say something about the proof, due to the fact there seems to be still 4 minutes left. So let me not go into the details too much, but the idea is that it uses ideas from thermodynamic formalism and stuff like that. So where does all this come from? Well, if you wanted a subshift of finite type, which are always good things to have, then you need an alphabet and you possibly need a transition matrix. So where do these come from? Well, the alphabet is going to be the set of saddle connections. That is the paths that go from a singularity to another singularity. Or if you've only got one singularity, the paths that go from the singularity wind around and come back. There's countably many of them, so it's a countable alphabet, and then you're going to have a transition matrix associated to that, perhaps. Here he is. So what we want to do is introduce a transition matrix. So how do we do that? Well, we have a singularity and another singularity. We allow we put a 1 in our transition matrix precisely when you're allowed to go from one saddle connection to another and it forms a geodesic. It doesn't go backwards the same way you came. It doesn't go back at an angle less than 2 pi, anything like that. It's a genuine, honest-to-God geodesic. And then what you want to do then is incorporate some information about the geometry. That's the lengths of the saddle connection. So you take your matrix and you stick in the values which are exponential minus the length of the saddle connection according to one of the axes. And maybe put a complex variable in as well. And then what happens is that if you have some sort of complex function which keeps track of the lengths of zigzagging geodesics, then you can write it in terms of this infinite matrix. There's an expression at the bottom. So this is kind of like symbolic dynamics, and the thing on the left is meant to be a bit more geometric. And so by studying the thing at the bottom, by knowing something about the matrices, you could hope to say something about this complex function and thus deduce information in some appropriate way. Let me just go to the next slide. So we have our function, which has packed together all this information about lengths of saddle connection paths. It has various properties. In particular, it has a simple pole, a value which corresponds to the topological entropy, which is a quantity we're sort of interested in. And if one knows one of the approaches to proving Margulis's theorem, then that uses complex functions, and you can just do it by analogy. Or if you wanted to do the rigidity result, you wanted to show that the topological entropy meant something specifically for these special surfaces, then you can use the characterization of the entropy using this complex function, and thus by the matrix to say something. And then there's some messing around. There's always messing around in calculations. I always hate that bit. And then one does stuff. Oh yeah, so the interesting part is that you want to use some number theory, and it's actually a result of Montgomery that's kind of useful here, because when we were characterizing the entropy, we characterized it in terms of a pole for a certain kind of complex function. But saddle connections, the paths that we zigzagging paths between saddle connections, well, we can write it in terms of an expression here, in terms of just a sum over, well, maybe single saddle connections, or in fact just lengths of vectors moved by a lattice. So it's just a single summation. And then this is very close to a result of Montgomery, which is written there, which tells us where the equilateral triangle stuff comes in. So it's a result on lattices. But he says that for certain kinds of functions, you get them minimized in the context of these series for lattices at these triangular lattices. And it just translates by messing around into this expression I had before. And then the only complication is it's not quite in the right form, but there's a result by a guy called Betterman, which I rather like because it sounds like Better Man. And he showed that it doesn't matter if you've got a square up here, you can get rid of it and you still get the same result. So you can shift it into the context we're interested, and indeed I think that's all I have to say about these things. Thank you.